Good afternoon, everyone. Today I'm going to speak about oceans from space and what I call the true final frontier. I'm going to cover these contents. So first I'm going to talk a bit about me. I'm going to explain why I call it the true final frontier. Then I'm going to explain why this is important, this type of research. And finally, I will talk you through my contribution. So this first slide is normally in most of my presentations. So I'm from Granada, a very beautiful city in Spain. And here you can see a picture of the Alhambra Palace. So I would totally recommend that if you haven't visited Granada, you put it in your list of places to travel to whenever we are allowed to do it again. More about my background. I'm a civil and environmental engineer, and I did my MH in the University of Granada in Spain. And after that, I was really enthusiastic about coastal engineering and academia, and I decided to do a master in science in environmental hydraulics because my goal was to stay in academia. But funny enough, after 1 year of doing these masters, I was like, no, this is not for me. I'm ready to go to the industry. And I was really lucky, and I got a position at HR Wallingford, which is a consultancy company based in Oxford. And I was there for a bit. But after that, I changed my mind again, and I decided to apply for a scholarship to do a PhD. And that's what brought me to Edinburgh. But again, this PhD was a joint PhD between Edinburgh and Granada. And what was initially a 6 months visit became 6 years. So here I am, essentially. So yeah, after my PhD, I got a postdoctoral research associate position. And after that, I got a Chancellor's Fellowship, which is my current role. And my research focuses on data-driven innovation, particularly space and satellite data. So why am I going to speak today about the true final frontier? Well, some of you, especially those of you that are fans of Star Trek, when you saw the title of the talk, might have thought about one of the films of Star Trek that has a very similar title. But unfortunately, my research is not about Mr. Spock. I wish. It's more related to the image on the right. So in the right, you can see a multispectral image from the Caribbean. And it's a very beautiful image. But there are many issues in that image. And the thing is that you might have heard that people say we know more about open space than about the ocean. And that, of course, is debatable. But it's true that there is not a lot of research going on in the ocean, in the study of ocean from space. And I said that in this image there are a lot of issues because despite being a quite clear image, well, we have certain issues that are going to affect the research or the information that we can extract from the image. So in this image, there are not just the pixels that you see or the information containing the pixels that you can see. There is much more information that we can use for research. So if this was an image from a phone, let's say, you would normally have 3 channels. You would have red, green, and blue. In this case, this image might have hundreds of bands, what we call bands like that. So imagine the amount of information just contained in just a simple image. But the problem of looking at the ocean is that in this case, we are not just looking at the ocean. We are looking at the ocean plus the atmosphere that is in between the satellite and the ocean. And of course, the atmosphere has water vapor, for example, that is going to change the way we look at water. Water moves, which means that the light that is reflected by a portion of sea is going to be different to another portion of sea where the wave is reflecting in a different way. Another very obvious issue with this image is that the clouds we have, if we are seeing clouds, that means we are not seeing the ocean. So clouds are not our friend. And finally, there is an issue, especially for those that work in coastal areas, which is called land adjacency issue. And is that pixels very close to the land are going to be contaminated, let's say, by the signal produced by the land pixel. So what we are seeing in the coast is not exactly what is happening on the coast, on the coastal waters. So you see that there are a lot of things to think about, but that's not the only problem. There is also a problem about resolution. So in this image, we are looking at the Gulf of Alaska, and the image is from a satellite called MODIS Aqua, and the resolution is 1 kilometer. And you might think, 1 kilometer, it's not too bad. And actually, this image is quite pretty. We are looking at a derived product of chlorophyll. So we see patterns, we see eddies. It kind of makes sense, right? So probably we can do a lot of stuff with this product. But the reality, if you are interested to work in coastal waters, is this. So in this image here, at the bottom, we can see leaf docks, and North Berwick is on the right. So this is essentially the Firth of Forth. And these pixels, this is the same satellite as I was showing before. The pixels are still 1 kilometer by 1 kilometer. But now you can see how, at a coastal scale, the information that before looked very nice, now is quite problematic. If we are interested in understanding what's happening around Edinburgh, we don't have information, or the information we have is very, very low resolution. So this is a massive problem. But there is also another problem about quantity. So to give you an idea, there have been a bit more than 20 ocean-specific public satellites, so satellite missions. So with public, I mean those sent to space by national space agencies like NASA or the European Space Agency, for example. And these were sent just towards the end of the 1970s. In comparison, at the moment, currently in orbit, there are more than 100 satellites that focus on land and atmosphere. And they started about 30 years before ocean was of interest. So you can see how there is much more research money going into land and atmosphere studies, and oceans are kind of left a bit behind. So that's a problem for anyone doing research in this area. But of course, the question is, why is it important to be able to look at oceans from space? Here I put some of the general issues that we can look at from space. The most obvious one is sea surface temperature, and of course this is very important for climate change studies, same as sea level change. It's two things that we can extract from satellite data and that are very critical to understand ocean acidification, how things are changing in our planet, how we are impacting our planet. Sea surface color can also be measured from satellite, and it's mainly used for chlorophyll historically. And chlorophyll is linked to primary production, and this is very important as well to understand climate change impact. As we'll say later, I'm using sea surface color for another purpose, which is linked to salinity estimation. But another option that we have from satellite is to map coral reefs or seafloor geology, which is also very interesting. Weather is one of the main purposes of studying the ocean from space, because weather models can be improved a lot if we have information about the ocean. Tracking marine mammals is another topic that is starting to be very important now, and actually there will be a PhD student starting in October, and we are going to track whale strandings from space. So that's very exciting. And finally, there is a lot of interest in terms of search and rescue. So as you can see, there are many different topics that are all observable from space in the ocean. So why am I doing this, or what's my contribution to reaching this final frontier? Well, for those of you who know me, I'm a bit stubborn. You know I'm a bit stubborn. And essentially, I call the can't do's the fuel for my research. So imagine when you speak with somebody that has a lot of expertise in a given area, and you say, oh, I'm interested in doing this research. And they come to you and they're like, well, that's impossible for these many reasons. So why would you bother? So the first time I said that I wanted to study salinity from ocean color, there were a lot of issues, of course, to start with. And people were saying things like, there are not so many ocean-specific satellites, which is true. And if you want to look at coastal areas, as we saw before, it's even worse, true as well. Salinity cannot be seen from ocean color, it's also true. So if you imagine yourself cooking, for example, you are boiling water and you add salt to the water, the salt is gone, you cannot see it. So it's the same in the ocean. And of course, there is not enough data in general to reach any conclusions. So that's a lot of problems to face to start with any piece of research. But then, as I said, because of the way I am like, well, it's difficult, so I should probably give it a try and see how it goes. So to all of those kind of negative assumptions, then I come with all of these questions. So, okay, there are not enough ocean-specific satellites, but what if we use other satellites that are not thought for the ocean, but we use it for the ocean? Let's see what happens. Salinity cannot be seen through water color, but have you tried? What if we try and see what happens? And okay, there is not enough data from satellites in this topic, but what if we use a lot of data from other sources? And the thing is that in the ocean, there are a lot of people doing measurements all the time. So why don't we use that? And that's actually how my research on measuring sea surface salinity and sea surface temperature at high resolution for space started. And so in the ocean, there is a lot of information, as I said before, specifically speaking about salinity and temperature. The most common information that we have comes discretely, so it comes from local buoys, for example, or vessels, research vessels. And at the bottom, you can see figures of different platforms, what we call platforms that measure stuff in the ocean. So the first one on the left is an Argo buoy. So essentially, you can throw this from a vessel or even from a plane, and it will go down to the seafloor, it will drift, and it will come up at some point, and it will be collecting information on salinity and temperature, among other things. The second image is a buoy, so a standard buoy that will be moored somewhere in the sea, in a fixed location, and it will be transmitting data. The third one is a glider, and this is a bit like a, well, it will have a pilot, so there will be a person in a vessel or somewhere nearby deciding where the glider goes or programming where the glider goes, and the glider will be going around taking measurements. And the last one is CTD, which stands for conductivity, temperature, and depth. And those black bits are bottles, literally bottles that will be taking measurements of, they will be taking sections of portions of water, and that will be analyzed at different depths, essentially. So there is a lot of this around the world. But of course, the problem with this is that they are discrete, they are localized. They will be taking measures in the patch of ocean where they are located. And of course, there are numerical models, and the numerical models are normally very good, but they need boundary conditions. So they need actual in situ data to say, okay, this is what the temperature or the salinity is in this point. Is that right? Are you modeling this correctly? And the same, they need validation data. And at the same time, there is currently satellites that give us information on salinity and temperature, but the resolution is terrible. So, for example, SMOS is a satellite that gives you salinity, but the resolution is about 35 kilometers, so really, really low. And for temperature, it's a bit better, but it's also in the range of kilometers. For example, the one that MODIS Aqua gives us. So, as I mentioned before, we need much more near the coast. And that's where the idea of this project comes. So I decided to use this satellite called Sentinel-2. And Sentinel-2 was not thought, it's not a built for purpose for the ocean satellite, but it can do the job because it covers the oceans. The resolution of this satellite is ranges from 10 to 60 meters, which is very, very good. And the revisit time is 5 days, which means that if the satellite goes on top of Edinburgh today, it will be going on top of Edinburgh again in 5 days. And Sentinel-2 started transmitting data in 2015, so we have some years of information. It's a multispectral satellite, which means that it has 13 spectral bands, so it will have the standard red, green, and blue that your smartphone camera has. But on top of that, it has another 10 bands that provide information on other parameters, like shortwave infrared, for example. And it has other information like cloud masks that gives us a lot of power to do research. So I like this picture because it kind of shows the different bands as if they were stacked in a way. So they are taken and they are stacked in a final tile that is called, or a final image. And that's more or less how it's easy to imagine how multispectral satellites work. So, okay, I have the satellite data, but of course the satellite is not measuring salinity and it's not measuring temperature. So how do I actually infer salinity and temperature from the satellite? The next thing I discovered is Companicus. So Companicus is a program from the European Commission that essentially collects information from different providers all over the world. And it collects information about in situ data, so data from the buoys, the gliders, and the other stuff that I showed before. And as an example, in this figure, you can see all of the platforms, and platforms are those buoys, gliders, etc., since 2015. So there are more than 14,000 buoys, vessels, etc., taking information that is available for us for free. And that's super good, that's super sexy. But of course, to do this research, there is a lot of need for computing power. And for that purpose, I work with Google Cloud and the Google services because you can access Google supercomputers also for free. And that means you don't have to download any information into your computer, which is very, very important, especially when you work with satellite imagery, which is very heavy. So, for now, I have satellite data, images, and in situ data. So, information from buoys about salinity and temperature all over the world. So, how do I match these two things? How do I infer salinity from images? And of course, there would be a relationship, or I wanted to test at the beginning if there was a relationship, but that relationship can be really complex. So standard methods didn't work. And then the approach was to use a neural network. And for those of you new to this field, neural networks are a type of machine learning algorithms. And essentially, they work in a way that imitate the way our own neurons work. So essentially, we will have a set of inputs. There will be some activity done on those inputs, and then there will be an output, a result of that activity. The concept is very straightforward, and the mathematics behind it, they are also kind of basic statistics, but the power comes when you put together a lot of these basic statistics. It becomes something very, very powerful. So to give you an example, a neural network works more or less like this. So in this example, we have an image of a doggy, and we are asking the neural network to tell us if it's a dog or a cat. So our input is going to be that image. There will be a set of hidden layers that we program, but we don't see what they do. And the output, we know it has to be, is it a dog or is it a cat? And for the neural network to work, essentially, we have to give it a lot of information, so a lot of images of dogs and cats. And then we need some kind of expert, so a person, for example, saying, this is a photo of a dog, this is a photo of a cat. So we train the neural network to understand the features of a dog and the features of a cat. So that's kind of the general idea behind a neural network. And in my case, my neural network does the same thing. Instead of a photo of a dog, I have the bands from Sentinel-2. So I have all of the spectral information. And I will have, again, hidden neurons, and my output will be temperature and salinity. In this case, the temperature and salinity from the in situ platforms from Companicus. So in this way, I'm kind of finding a relationship between satellite data and in situ data. And when I started looking at all of the information from 2015, I had about 65,000 data points. So imagine a matrix of 65,000 by 65,000. It's just really, really massive. It's really good for machine learning. It's exactly what you need. But of course, not everything could be easy. And then the real problem is matching the data. So essentially, matching the data means that I have platforms, I have boys giving me information every 30 seconds. Some others give information every 3 hours. Every platform is different. But on top of that, I want to be looking at that platform when my Sentinel, my satellite is looking at it. So I need to make sure that I match the information from the buoy at the exact time that my satellite is going on top of the buoy. So it's quite tricky because the satellite only goes on top of a given buoy, let's say every 5 days. So there is a lot of data matching going on there. And essentially, the problem as well is that salinity and temperature change in the ocean, and that's the point of doing this research. So at the end, I decided that a sensible time was to kind of leave 1 hour in between. So let's say 1 hour around the time that the satellite passes on top of a given location, and I would take the closest measurement from the buoy in that hour to make sure that I'm taking a photo of a given salinity and temperature concentration, and that's as correct as it can be. So of those 65,000 points that I had at the beginning, I ended up with 9,000 by doing this matching process, which means it's an 85% reduction. So 9,000 points is still very good, but it's quite depressing, as you can imagine, when you start with 65,000 and then you have to match all of the information and you end up with much fewer information. So that's a matching process. And once that's done, you can train your network. And the results actually were pretty good. So in this image, on the left, you can see temperature, and on the right, salinity. And the image, the color bar, shows the error. And in this case, the error is defined as the difference between the predicted salinity or temperature and the expected salinity or temperature. So expected is the value that is given by the buoy or a given platform. So the real, let's say the real value. And the results are pretty good. The darker those dots are, the best the result is. The better the result is. And essentially for temperature, the result was around 0.4 degrees Celsius. And for temperature was around 0.2 PSUs, practical salinity units. And you will say, okay, 0.4 degrees Celsius, we can understand what that is because we measure many things in Celsius, so that makes sense. But what is 0.2 PSUs? And it's a thing that oceanographers measure salinity in a very specific manner, but PSUs is more or less equivalent to grams per kilogram. And to understand how good or how bad 0.2 grams per kilogram is, I have a bit of a proof of this. So a kilo of water is more or less a liter of water. So in this bottle here, I have a liter of water. And the normal concentration of salinity in the ocean is about 35 PSUs, which is equivalent to 35 grams per kilogram. So in this shot glass that you can see here, I put 35 grams of salinity, of salt. So in theory, if you mix these two things, the water, the salty water that you get here would taste like the ocean. And to understand how small the error is, I put in this other shot glass, which is the same as the initial one, 0.2 grams of salt. And I'm not sure you can see it, but it's essentially nothing. It's literally a pinch, a bit less than a pinch of salt. So compared to the original 35 grams, you can see that the error that we are getting is really, really good. It's essentially we are estimating salinity in the ocean with an error of less than a pinch of salt from about 800 kilometers from the sea. And I would say that that's a great achievement. So, of course, the image that I showed before is comparing the results to every platform, the given error within a given buoy. But the next step was to apply the results of this neural network to a whole satellite image. And in this case, we can see the Bay of Cadiz in Spain, very close to where I'm from. This is in the Atlantic Ocean, and Gibraltar will be towards here. I don't know if you can see my cursor, but towards the bottom right corner of the image. And you can see how we have a river on the top of the image, and we can see how the river has fresh water that is interacting with the salty water of the ocean. And even more, we can see eddies, we can see mixing patterns, and that's really, really promising. And in the right image, in the temperature one, well, we can see how in this case, the water from the river is slightly warmer than the one from the ocean. And well, we can see an alongshore current that is a bit colder coming from the Atlantic. So there are a lot of interesting features that are being kind of highlighted by using this method. But this works in many other different locations. It works everywhere that I've tested so far. In this case, we have on the left an image from the Bay of Cubay. And we can see how there is a river here and an estuary, and we can see how the mixing makes sense, the mixing patterns. But my favorite image for sure is the one on the right from Canterbury in New Zealand. And if you pay attention to the bottom left of the image, we can see a very interesting set of eddies forming. And they look a lot like a phenomenon that happens in hydraulics called Kelvin-Helmholtz instability. And this happens when it can happen when you have two fluids with different densities, and in the interface there is this shear stress or this velocity difference, and then these eddies are created. And I found it really, really exciting that we were able to see this from an image that originally is just a blue image, a beautiful blue image of the ocean. There is a lot of interest about this, and here I have listed some of the people that want to apply this to their work. One of the industries is the salmon producers, because they see a lot of potential for remote monitoring, but also Crown says Scotland is interested in terms of offshore wind farm location or co-location with fishing industries, for example, and also accessing and assessing new sites. So being able to assess the quality of a site without having to send a vessel there. The Scottish Environmental Protection Agency is also interested in terms of tracing pollutants, because it seems like pollutants are linked to salinity. And finally, the National Oceanographic Centre are also interested in testing this, because high-resolution data anywhere in the world that is free, essentially, it's something very attractive. So that's the science for me. Here I wanted to introduce you to my team, which I'm very proud of. And of course, what I've showed today is my own research, my own topic, but of course, all of these people here work in different areas, all of them in coastal and environmental remote sensing. So we cover shoreline management from remote sources, shoreline understanding, water quality indicators, lake dynamics. So a lot of different topics, and they are all very, very enthusiastic and working really hard to explore this new frontier, essentially. And that's everything from me today.